So actually I started the recording, the video going to be recorded. Some students contacted me saying that they got contracted with COVID. Not many, few of them, 3 or 4 I believe. So it's good to record the lecture and make it available to everybody. They won't be able to come for this week and a few days from the next week as well. So just to recap our stage, I believe we completed seismic refraction technique and we did 2 labs on that part, on seismic refraction. Today we'll move to a new chapter. It's one of the most interesting chapter. I will have also 2 probably labs. One of the labs is a simple paper lab, manual lab. The other one is using a software. We'll use software to try to do some velocity analysis and stacking. What are these terminology? These are the things we're going to learn in this new chapter. Most of you did really great regarding quiz 1. I think according to the plan or to the curriculum, next week supposed to be a quiz as well. Am I right? Could you remind me if you know the curriculum? Isn't it? In week 6, this week. So let's postpone it to next week. Let's make it next week. So still you're going to have some time to review and prepare yourself for the quiz. Again, it will include only 1 chapter. Or there's 2 chapters, seismology and seismic refraction. It will include 2 chapters, the next quiz. And regarding the midterm, it was planned either to be in week 8 or week 9. Week 8. So let's have it. This is week 6. 2 more weeks, then we'll have the midterm. The midterm will cover up until this chapter, seismic reflection. Week 8 أحسن. Let's go according to the plan. I think yes. Similar to quiz exactly similar to what you had in quiz 1. But it will cover 2 chapters instead of 1 chapter. So we'll have a chapter which is about earthquakes. Also the other chapter, seismic refraction. The last chapter we finished and concluded. Today we'll move to a new chapter, seismic reflection. When I start lecturing or discussing, you'll find that there are some advanced terminologies, advanced probably mathematics. That's fine. I will not ask you during either exams or in any assessment component how those equations were derived. That's not the point. You need to understand how to use them and either for exam or a lab component, use them to solve the lab. We'll have 2 labs. First of the labs will be about how to get the velocities from seismic shot gathers, seismic reflection shot gathers. That's going to be in this week, during this week. So why seismic reflection? Why it's important? It's very important because it's widely used in oil industry. And many of you actually are either geologists, petroleum engineers, oil prices are increasing, employment rate or employment possibility is getting better and better, especially for oil companies. They started hiring graduate students either from SKU or from abroad or from other universities in Oman who have a background either in geology, geophysics or petroleum engineers. This is actually the technique most often used in oil industry. 95% of the time it's used in oil industry. And I will let you know that why that's the reason, why it's so common to use seismic reflection technology. The basic principle is to send energy and get them reflected back. So before we start, let's discuss some points. It's easiest in terms of acquisition, but very complex when you do processing. The processing part is really very complex, very time consuming, computer intensive. I cannot do processing using my laptop, seismic, especially for heavy data. And that's actually the reason why they say, according to some statistical data, that seismic data processing consumes almost 30% of the computer power around the world. The computer power, 30% is used in processing seismic data. Maybe the percentage nowadays changed a bit because we are getting new technologies like AI, artificial intelligence. They also consume a lot of computer powers. But the most advantage thing about seismic reflection is that it gives you an image of the Earth. The image you receive or obtain, the final one, is closely resembling the real Earth. It's almost like a screen capture of some cross-section. That's why it's so useful. It's useful for shallow investigation as well as deep investigation. It's widely used in oil exploration. Probably you have heard of Fahoud field. Have you heard of Fahoud field? So they started exploration in Fahoud field long time ago. The first time they drilled, they missed the well or they missed the reservoir. The reservoir is an anticlinal feature or structure offset by a fault, a large fault. So if this is a reservoir where you think the oil going to be accumulated, that's the foothold wall and that's the hanging wall. In the foot wall, here probably, that's the oil-water contact. So geologists went to the site, did geological investigation, geological mapping, and according to their investigation, they thought that this is the area to drill. That's true. If there were no fault, they didn't know that there is a fault. They can't tell that there is a fault because they are doing surface mapping only. And they missed the field. They went away. They didn't drill another well. They said it's empty. There is no oil in that specific field, Fahoud field. Fahoud field, by the way, is still producing up until now, from 1965. Up until this date, it's producing a lot of oil. And there is another field called Ibal field. The structure is very similar to Fahoud field. Qarn Alam field, it's a bit different, but it's also similar to Fahoud field. How they discovered that there is a fault? What they used? Seismic reflection. Seismic reflection actually was the technique to discover that there is a fault. And the difference was almost just 50 meters. And that well is up until now is there. That dry well they drilled and found nothing. You go to Fahoud, it's a landmark there for the visitors, for the guests to know how technology developed through years. So they came later, once they discovered that there is a new emerging technology, seismic reflection, can reveal a detailed structure of the Earth required. Basically, easy technique was that there were no 3D seismic. Nowadays, we are using 3D seismic, whereas the data they acquired in Natah field were just 2D, and they found that there is a fault we're supposed to drill here. That's the area we're supposed to drill. So it gives you detailed stratigraphic features of the Earth. Basin analysis, it's a course, advanced course in geology. Sequence stratigraphy, this, I believe another course, sequence stratigraphy. It cannot be revealed, cannot be done exactly or properly, except if you have great seismic data, especially 3D seismic data. Knowing how the faults are oriented, how the complex fault structure is there, cannot be informed unless you do seismic reflection studies. Fault, other geological investigations, how much is the oil accumulation in the reservoirs. It cannot be determined exactly, but you can make some guesses. You can make some guesses. Usually these guesses are very close to the reality. How I can tell exactly how much accumulation of oil is there, you cannot tell unless you drill one well. At least you cannot tell exactly or very accurately unless you drill a well. But at least seismic, from the structure, from the velocity analysis, from detailed analysis, you can tell whether there is oil accumulation or not and how it can be done. There is this thing we call bright spot, flat spot. Those are some features in seismic reflection data which can tell us whether there is oil accumulation or not. We'll investigate some of these features, what we call bright and hot spots. So it's very popular. It gives you an image that's very close to the real geology. That's very interesting. If I go just, let's make some Google search. Moving a bit aside from the slides. Let's say, right, seismic section. Internet is so slow here. So this is a seismic section, what you see there. Small images of different seismic sections. Let's see one example, and I will ask the geologist some questions then. Let's go with this section probably. So that's good seismic section. That's what you see is a seismic section. If I ask you a question, what do you think is this column? Why there is no data here? Huh? That's C. That's C column, sea level. Where do you think is an unconformity? What level is an unconformity? Is this? Where is an unconformity? That's an unconformity. This is a seismic section, but it's resembling truly a geologic section. What are these? These are layers. That's a layering. They got folded, faulted. That's a syncline. So this is the final product we need to produce, give to the geologist. As a geophysicist, that's what we are asked, to produce an image similar to this, or resembling this image. This is a 2D. It could be 3D. In 3D sense, it's a cube. You can slice it in any direction. You can take a slice here. Probably you will get, if the geology is very complex, it's changing a lot, you probably will get a different image, slightly different image. You can take even a time slice, because this axis, the y-axis, is not depth, is what? Time. Time, the energy goes, get reflected back. There is no reflection in the water column because the velocity is the same. The velocity and the density, the acoustic impedance, the property we'll study, is the same. So there is no reflection, whereas I get strong reflection at the sea bottom. The change in velocity from water to rock is large. I get a large reflection. The energy get reflected back. Here also I get a strong reflection. That's an unconformity. And I'm seeing some progradational features, other features. I'm not expert in geology, so maybe that's a reason PDU is employing geologists to do seismic interpretation. What's seismic interpretation? Seismic interpretation is basically following any of these reflections or reflectors. So if you think probably this area is of interest to you, you think that there could be an oil accumulation in this area, so you try to track or map this specific reflector. Try map it, not by pen. All days in 1960s, 1970s, they were doing it by pen. They get this printed, put it on a table, the interpreter start following a specific interface, probably this interface. They try to follow it, pick. That's how it has been done long time ago. But nowadays, because there are softwares, one of the useful softwares we have is Petrel. It's a trademark of Schlumberger. It's widely used in many oil companies, PDU, Oxy, other companies. So they follow this by a mouse. That's one section. If it's 3D, so you can move another section with an increment, another section. What you keep doing? Following this unconformity. You can take a time slice. You can take another section perpendicular to this section, because it's a 3D, a cube. It's almost like a cake. You can cut the cake in any direction. You can cut it even horizontally. In here what we call a time slice, because this axis is time. It's not depth. However, we can convert it to depth as well. Can be converted to depth if we need. Back to the slides. So why it's very important? The reason being, it produces an image that resembles the true geology. It looks very similar to the geology. So it started in the beginning of 90s, last century, specifically for oil and gas industry. The initial development started in USA. The recent science all developed in actually USA. And initially it was simple, easy, 2D seismic. They haven't started with 3D seismic. Things were not computerized. It's hard to save a lot of data. In early 1980s, they moved to computerizing data, digitizing things, those images, the one I showed you just now. Nowadays, we can do interpretations, other things in computers rather than on printed papers. So it was very expensive initially because things were not as easy as it is now. How we do marine acquisition was even very complex, not easy. Nowadays, marine acquisition is very easy. Most part of the oceans were covered by seismic surveys because it's very cheap to acquire seismic data in marine. Why it's cheap? You just tow your equipment behind a ship, large ship, or what they call a vessel, seismic vessel. You tow your acquisition system and let the ship move. It keep acquiring data and receiving data, saving them in tapes, bringing them back to the office for geophysicists to process. Processing is very complex in seismic reflection analysis. So as I said, it's very important or very popular because it produces an image of real seismic cross-section. It gives you very high resolution. The resolution is way higher than the seismic refraction technique. Another important parameter is that there is no seismic velocity inversion. It can still work if there is a layer of lower velocity than one above of higher velocity. If this behavior happens in a geologic section, seismic refraction will not work, whereas seismic reflection still can work. It's way cheaper than drilling blindly. An exploration well in some place, especially if deep marine, it might cost you 20 million, 15 million, or even more, especially if it's an exploration well. The first well you drill in an area. Whereas seismic study whole of the area might cost you only 5 million or 10 million, depending on the parameters you need, how much resolution, and etc. So seismic technique is very cheap. It's easier to actually do seismic rather than go blindly drill everywhere. But sometimes even seismic cannot work. For example, PDU, in some places they are drilling blindly. Seismic reflection cannot work great in areas where there is salt domes. Salt dome. Salt layers. Why is that? Because internal structure of the salt cannot be inferred easily. You will not get layering. Seismic works best in sedimentary rocks, in sedimentary environments. It's very easy to acquire seismic or process seismic data in areas where the rocks are horizontally layering. If it's very complex, the structure is difficult, then the processing becomes very, very difficult. So let's discuss what's the difference between seismic reflection and the chapter what we studied last time, seismic refraction. First of all, resolution. You get just velocities, layers. Did we get any layering, any reflections? No. In seismic refraction technique, you never ever get where are the layers, how detailed are layers. Whereas in seismic reflection, we get almost a real image of the subsurface. That's very advantageous in seismic refraction technique. Another thing, in the seismic refraction, there is a caveat which says that whenever there is a lower velocity, deeper lower velocity than a shallower higher velocity, seismic refraction cannot work. Seismic refraction usually gives you the great or big picture, crustal features. There's a crust beneath a mantle. It's a big image. You cannot go very detailed. You cannot reveal very small velocity variations, whereas this is very possible in seismic reflection technique. And during the last slide, we said, if I want to go and investigate a depth of 10 meters, how much is the separation between first and last geophone? 100. 10 times, whereas it's 1-to-1. The relationship is 1-to-1 in the case of seismic reflection. If you want to investigate 1 meter, make the separation only 1 meter. If you want to investigate 10 meters, even zero separation can still work. Because the energy just goes down. The source and receiver are here. This is a source, receiver. The energy goes to any layer. What you will receive in terms of data, in terms of a geophone, if assume that this is a geophone, it receives energy. The energy gets received back. What I get here? A pulse. Three different pulses. That's if I have only one geophone. If I have multiple geophones, I stack or put or align these traces side by side and get a geologic feature, a geologic section. That's how it works. There is only one drawback. The only drawback is the processing power. You need to do a lot of processing in seismic reflection to come to this final stage. Whereas processing was very easy. I gave you a software to do the analysis during the last lab. That's easily available. You can get a lot of different softwares in seismic refraction technique. Whereas there is no single processing software available for seismic reflection freely. No, you cannot. You have to pay, and you have to pay a lot of money. None of them are free, either for academic purposes or especially for commercial. So if you are owning an oil company, you want to use or process seismic data, it's impossible. I believe when I finished my MSc program, there were a fellow students of mine. They built their own company. They created a company. The main task of they were doing in their company was seismic processing. But they were graduate students. And the software they used wasn't free. They were monthly fees to the company they purchased the software from. So the processing is the most difficult part in seismic technique. So how it works is similar to echoes. What's an echo? Sada. Have you heard of echo? Have you ever heard of your own voice coming back to you? That's an echo. It's similar to the same technique. It's echo sounding. I'm sending a sound wave or whatever type of energy, getting it reflected back to me. So let's assume that this is a ship. The ship toys behind it a source and a receiver. Has a source and a receiver. The energy goes down, seismic waves. The energy is moving as seismic waves. That's the seafloor. That's a different layer. One layer, third layer. There are three different layers. So what happens? The energy reflected back, get reflected back whenever there is a change in velocity and density. Whereas the case, what was the case for refraction? We needed only a change in what? In velocity. No, here we can even reveal the density variations in the rock using seismic reflection technique. So whenever there is a difference in the rock property, in this regard, we are concerned with velocity and density of the rock, the energy get reflected back. I get three different reflections. So that's the first reflection. The ship keep moving. It sends another pulse and another pulse. I get what I call traces, different traces. A firing has been done here, another one here, another one here. And those three pulses are actually a reflection from different interfaces. That's what you get. You can display them in different formats. That's one of the formats we call wiggle format. We'll see the examples of format later in this chapter. So that's how I display them. If you are a geophysicist, you can tell that this is one layer, that's another layer, that's one more layer. We have three different layers. So this is how it basically works. So what are some caveats? What are the drawbacks? They are not certain drawbacks. They can be solved with processing, intensive processing. The data I get, they are not the real data. They are what we call raw data. We need to do some processing, similar to what we do, for example, in seismic reflection. Processing is very intensive. So one of the caveats is that the y-axis in the previous image you have seen, this axis is what? Is time. It's the energy sent and received back. How much time it took for the energy to return back. So the y-axis is not depth. It cannot easily be calculated. It's not easy, especially for complex structures. You cannot say, okay, I multiply my time by certain velocity or divide by certain velocity, I easily can get to depth domain. It's not that easy, especially if the velocity is varying from one location to another location. So it's very complex. Another thing, the source, that's what I assumed. This is my source receiver location. I assume the energy, I always assume the energy is coming from down below. But the energy can come from any point. It takes the shortest path. The energy comes from the shortest path. That's what we call Fermat Principle. So if I have a layer like that, and this is the surface, let's assume I have a source and the receiver here. What I assume the energy went like that, get reflected. That's the midpoint. That's how that seismic reflection works. But that's not true because the layer is dipping. The layer is dipping. From where the reflection comes then? What is the shortest path for array to go, hit this interface, and get reflected back? What do you think is the shortest path? Is the one which is perpendicular to this interface. So that's the one. That path is the shortest path. So I get a reflection at exactly, if I'm dealing with time domain, that's my trace. Let's use another pen. I get a reflection here. Which is not exactly true. The layer is at that depth. So how this can be solved? Can it be solved? Yes. It's not easy to solve it, but it can be solved using some techniques. Another problem usually we find is multiples. I talked about multiples. Multiples, what do you think are they in geophysical data, in seismic reflection data? Noises. They are noises. Multiples are noises. Don't need to write this because it's already mentioned in Introduction Chapter, I believe. So multiples are noises. And what exactly are multiples? Multiples are basically more than one reflection. It's not the primary reflection. Let's take another example. So I have a source here, and the receiver is here. A simple configuration of one source and a receiver. Pair of source and receiver. So how multiple happen? What do you think about this energy traveling down and getting reflected back? Is that a multiple? No, that's a primary. What do you think about this one? That's a multiple. This is a multiple. That's a noise. Can we solve this problem? Yes. Can we solve it perfectly? Not exactly. Not exactly, but it's solvable. And that's the reason seismic data process, seismic reflection data process is a bit complex. How to remove these things is not an easy task. Companies like CGG, their main work or only work is seismic data processing. They struggle a lot how to remove multiples. They have whole teams just dealing with how to remove multiples. Not one person, many people trying to remove multiples from seismic reflection data. So multiple are noises. Multiple energy are noises. So what's the main difference? What I get? This is recording a trace. Am I right? So this is recording a time variation in energy arrivals. So I get one energy. It's not exact. This is depth. Whereas this trace is in time domain. I get some noises. It's not exactly perfect. I get one reflection. And after some time, another reflection. I get two different reflections. Which one is the primary? Which one is the secondary? Or sorry, multiple. The first one is primary. That's easy. The second one is multiple because travel twice. It takes double the time. If this is 1 second, this will arrive after 2 seconds. So that's one of the criteria. If I know this thing, I can easily remove multiples. So instead of thinking that this could be an interface, be cautious. Don't think that everything is an interface in geologic or seismic reflection data. So we could get multiples. That's a problem. That's a problem. However, those problems can be solved using seismic processing techniques. It's not like velocity inversion problem we have in seismic refraction data, which cannot easily be removed. I cannot do anything about seismic or removing or dealing with data where, or model, subsurface model where we have a velocity inversion. So how they look like and how we deal them, that's the thing we will discuss soon. There are other caveats, but those are beyond the topic or scope of this course. So this is the ray. That's what a deepening layer is. We assume that things are happening or coming below the interface. So we assume if I have a source, a receiver pair exactly at the same point, I think or I assume the energy is reflecting that from down below. If I have a source and receiver spaced apart, I believe the energy is coming from exactly in the midpoint. That's the shortest path. That's the shortest path, which is not totally true. It comes from perpendicular. That's the shortest path, what you see here. That's actually the shortest path. This can be solved. There are techniques that can solve this problem. And there is a course, what we call seismic data processing. It's the course I teach right now. We will do processing, such processing to remove these artifacts. And also we have multiples. What is a primary? That's the only primary we have. This is considered as a multiple. This multiple, which we have three different multiples. That's a multiple. That's an internal multiple. That's a pig leg multiple. You don't need to know the names. But which one you think of these three is easier to remove? What's your name again? You were my students in other course. Huh? Ammar. What do you think? Which one is the easiest to remove? واحد اثنين ثلاث. 1 2 3. Yeah. Why is that? It's same and it has multiple. The time for reflection is double the time of primary. So it's easy to guess it, easy to know it. Whereas this one are more difficult to remove. They cannot easily be removed using simple technique. There is a technique you will know if you take data processing course called deconvolution. Deconvolution. Convolution means complication. In terms of meaning, تعقيد. So how to deconvolve? It's an advanced technique, will not cover it here. But deconvolution itself can remove only this part or this type of multiple removals or multiples. Whereas those type of multiples will need a more advanced technique of demultipling. They are not deconvolution, they're called demultipling or demultiple, removing such complex multiples. They're complex because the time of the multiple is not multiplication of the primary. It's 2 times, it could be 3 times of the primary, 4 times of the primary. And multiples usually happen whenever we receive or the subsurface have a strong reflection. If the reflection is very large. What I mean by reflection is the energy reflecting back. So if I say there are 2 reflections, one, another one, which of these 2 reflection is of higher energy? Second one. Second has a higher amplitude. The amplitude from 0 is largest. Amplitude and power or energy are related to each other, proportionally related to each other. So this has a larger energy reflecting back. And why it has a larger energy? Why there is a larger energy reflecting from this? Probably there is an interface. A velocity contrast or what we call acoustic impedance contrast, because the velocity variation is larger. The physical property between this rock and the rock below is larger, is higher. So back to the image I showed you, we have seen that the seabed is clearly can be traced. You can't clearly pick the seabed, track it. If I give you a pen, ask you to track where the seabed is, you can easily tell where is it. Why is that? Why the seabed is clearly visible. Yeah, the seabed specifically, because the contrast in physical property between the sea column and the rock below is large. So I get strong reflections as the seabed. And what this will create, this creates some problems for me. So here is an example. That's a seismic section. This is a seismic section. That's where the acquisition happening on the top. Those are some noises. So that's what we call seabed. You see the seabed? Strong reflection at the seabed. very strong reflection at the seabed. What do you think are these noises? Why you get noises at the surface area?
Organisms?
No, another thing. No. Yeah, that's one. They have waves. There could be some waves. Those are waves. But they are equipment noise. Equipment themselves are generating noises. So if I throw something in the sea, what happens? It will generate waves. So those waves are the equipment waves or equipment noise. Can easily detect them, remove them. That's fine. This is the seabed. It clearly can be visible. If I ask you to track or pick the seabed, you can easily tell, oh, that's the seabed. Easily can be picked, can be tracked. Whereas if I ask you to track any other interface, it's not that easy because the physical property is not that much difference. Whereas the physical property is here is very, very large. So what this creates? This creates multiples. Strong reflectors, they are candidates for generating multiples. So what I see in if I ask you someone to trace these interfaces, seabed interface, that's the layer he gets or she gets. That's the layer of seabed in time domain. That's two-way time. It's not one-way time, it's two-way time because the energy goes down and gets reflected back. That's what we call two-way time. Whereas in seismic refraction, that's one-way time. It's not two-way time. There is two-way time. So this is the seabed. What is that? What is this interface here again? That's again, sorry, here. What's that? That's again the seabed. That's the seabed again. Why is that the seabed generated multiple? Because simply it is a strong reflector. It's a very strong reflector. It can generate multiples. This is an erosional surface. What do you see here? That's an erosional surface. It's also very strong reflector. So it generates some multiples. That's a multiple of this. Means the energy got reflected from seabed, hit the surface, went back again, and got received by, yes?
How can we differentiate between the seabed multiple and the old seabed?
That's the primary, that's the multiple. It's not easy. If you are a good geophysicist, you can't tell. But one way is, what's that? Multiple the time of primary. Double the time. If this is, let's assume how much millisecond, I'm not sure exactly, that's the double of this time. That's one way. Another way is to do, as I said, deconvolution or analysis, deconvolutional analysis. Before I apply deconvolution, by the way, there is some analysis I perform. I can tell them if there is any multiples or not, especially these simple multiples. Whereas interbed multiples, big leg multiples are a bit harder to distinguish. This feature, you will find it somewhere here. It's very close, similar to the feature you see up the erosional surface. That's a multiple. So this section, that's a seismic section, it haven't been processed properly. There have been done no good processing to remove those multiples. Any questions so far? Is it clear? Will not remove those multiples. So the good geophysicist, he can easily distinguish these problems within the geophysical data. Here I say that these are noises, geophysical noises, equipment noises themselves. I'm turning the geophones, or not geophones in this case, hydrophones, and those will create noises, waves within the surface of the ocean. And how we determine the structure internal of the Earth? We need to know its velocity. again, the velocity picking in any geophysical technique is very important, or seismological technique. So we need to know what are velocities of the subsurface and how this can be done. It can be done through a process what we call velocity analysis. And we can tell the velocity analysis by a technique called normal move out. A technique called normal move out. So in case if I have a horizontal reflector, I need to know how the energy travels, first of all, for the reflection case. So this is the source, and I have how many geophones? There are 6 different geophones. The model here is made up of 2 different layers. So which travel time is the shortest? The travel time, for example, from source to this receiver or from source to this receiver? Yeah, it's the shortest. It's closer to the source. The offset, the team offset is important here. The offset is smaller. The offset is larger. The offset is basically the distance from source to a receiver. That's the offset. The distance from a source to receiver, that's what we call an offset. So if I'm asked to know, if I assume that that's my model, I know what's the thickness, I know what are the velocities. That's an assumption I make. How I can calculate the velocities, for example, if or make what we call analytical data. How I can tell what is the velocity? Let's assume I take this example. The energy is traveling here to here. That's the path. First of all, do you think this path is similar to this downgoing and upgoing? Are they same or not? They are the same. Because a reflection, what's the angle of incident and reflection angle? They are the same. So this path is similar to this path. So using Pythagorean theorem, I can work out what is the velocities. What is, if I know the distance from source to receiver is x. What is half of this distance? Is x over 2. And what is this one? That's the h. What is the most shortest path, by the way, back again, away from the question right now, how we solve this velocity equation? What is the shortest path? What is the, But what is, at what location the source and receiver should be, so I get the shortest path? The same, yes. If the source and receiver are exactly at the same location. That's the shortest path. There is no extra time. That's the simplest time. So what if the source and receiver are exactly here? What is the velocity? What's going to be the velocity? What's going to be the velocity? What is the equation of velocity? Distance over time. So it's going to be 2h over t, or t equals 2h over v. So this t, this specific t, I call it t dot. T dot is the time of reflection where the source and receiver are at the same point. So using this Pythagorean theorem, I can work out what I call normal move out. So farther away, the time start increasing. There is an addition to this extra time. So it's the other times, a time at any other x point, tx equal t naught plus some increment in time, delta t. So that's the equation we try to solve. In this simplest case, I need to know the h, and I need to know at what is the x. X is known to me because this is where I located my source and receiver, but I don't know the h. Assume I don't know the h. This is how we can solve it. So back to this previous slide, instead of just 3, let's assume I have multiple geophones, many infinite number of geophones. And this is the data we get for 2-layer case. for simple one interface. That's the data I get. For reflection, if I have only reflection, refraction, direct and refracted. How the reflection will look like? A hyperbola. Do you remember that? A hyperbola. The intercept, this is T naught. So what is the difference between that and this one? 2. Because in this case, I had the source here and a lot of receivers. Whereas in this case, I have the source in the middle and 2 side geophones. The geophones are in both sides of where the source is. Let's go back. Geophones in both sides of the source. This type of acquisition, we call it split spread, where the source is in the middle. Whereas this type, where the source is one side, the geophones in one side of the source, that's called off-in. You don't need to know these terminologies. But anyhow, if you got questioned why there is why it's called split spread, because the geophone is in the middle. So the source is in the middle. There are geophones in either side of the geophone for 2D. This is a 2D. So this is a 2D acquisition. In 2D acquisition, the source and receivers, the source, one single source, and a lot of receivers, they should be aligned. What about the 3D? That's a source. Geophones can be in any orientation, anywhere. That's a 3D. We'll not deal for, at least for this course, with 3D processing or how to do velocity analysis for 3D. So this is what we call a hyperbola. That equation is an equation, or that line is an equation of hyperbola. It's not a parabola, it's a hyperbola. It's called a hyperbola. That's an equation of hyperbola. And we know what is a hyperbola. What's the equation of hyperbola? So if you use this technique at this specific time, at this specific location, the time is what? T naught. Apart, away from the source location, at a distance x, the time is how much? T naught plus delta t. There is an extra time. The time is increasing as we go farther away. So geophysicists try to know what is this time, because they need to bring this one and flatten it. This line, I need to flatten it. That's a reflection, supposed not to be like a hyperbola, whereas supposed to be a flattened layer. In reality, these are not lines like that. In reality, there are traces. So these are basically different traces. So this is one trace, another trace, another trace. There are traces, ignoring for the time being those energy. There are also reflection like that. But I'm not interested in this one. I'm interested on reflection. And that's a complexity also with reflection, because in refraction we are interested on first arrivals. This is a first arrival. This is direct. So I'm not looking for this first arrival. I'm looking for the hyperbola. There could be many hyperbolas, another one. So you make picking, similar to what we did in the lab, and draw a line. That's a hyperbolic line, a line of hyperbola. The time here is T naught. T naught can be calculated using this equation. So how we calculate the time here? At an offset x. That's what we will be dealing with. We need to find that time. So that time is basically the equation of hyperbola. It's equal to T naught squared plus x squared over v1 squared. What is the missing parameter here? What I don't know from my acquisition system? H is not there, at least for the time being. Huh? We don't know V. Because this is the T itself. From where you calculate the T? From this data. This is the data you got. These are your real data. I don't care about the H. I don't care about this H, which comes from T. I know already the T. It's T naught, sorry. T naught is calculated from here. That's the T naught. T naught is calculated from here, your data, original data you have. From where you get the X, even from your acquisition. You know the distance at this geophones, you know it. Because you lied out the geophones. You know what's the spacing between geophones. How far is the geophone from source? So you know that information. What's missing? Velocity. I need to determine the velocity of the subsurface. And that's what we mean velocity analysis. It's a whole topic or whole chapter in the other course I teach, seismic data processing. I'm still right now in deconvolution. How we do deconvolution. We just start. There is another chapter about migration, about many other chapters. So deconvolution is a chapter. Velocity analysis is itself a chapter in seismic data processing. We try to do velocity analysis, how it can be done. So those parameters are read from this equation of hyperbola. That's the equation of hyperbola. And we can simplify this one to this. So to know the velocity one, we use this equation. Everything is provided to us. We need to know, if we need to know the velocity, either this one or this one. So from where we came, let's make it very quick because I will not ask you these questions. The time is two-way time. We try to derive the equation I just showed you. These two equations, how they were derived. But keep in mind that I never ask you in exam or quizzes how they were derived. What is the T naught? The time where the source and receiver are at the same position. How it can be calculated? 2h, the energy goes down and get reflected back. That's where the offset is 0. At other offset, the time is different. We can use Pythagorean Theorem. We know already the x, and that's half of x. That's half. Ignore for the time being this equation. It's Pythagorean says h squared, that's h squared over this distance from here to here, it's x over 2 squared plus. Why I multiply by 2? 2 times, yeah, one and another, returning back. That's what we call two-way time. Why I'm dividing it by velocity of first layer? That's the total distance. Without this is the total distance. But what I want time, so I divide it by velocity. I divide it by the velocity of this layer, because this energy is traveling in this specific layer, layer 1. But, yes, is this helpful? Can I use this equation directly to derive the time at least? Why is that? We don't know V1, we don't know even the velocities, we don't know the H. How we can tell the time if we don't know the H, neither the velocity? So what we do is do some arithmetic operations. We do some magics. So square both sides. Square both sides of this equation, so square here and square the other sides. So this has been squared. The other side, if I square it, what happens? 4 divided by V1 squared, and the whole of this as well got squared. So h, if I square this part, what happens? I remove the square root. That's what happened. That's how is it. And try to simplify it even more, do some algebra. What I'm doing, I'm trying to simplify it, this term multiplied inside, 4h over v1 squared, 4x over 4 over 4, what happens to them then? Will cancel out. So this is the end product, at least. That's the end product. What do you think? It is actually 4h squared over v squared, but I can remove the square. Becomes 2h over v1. What is that? That's t naught. So what is this equation? T over this one, that's the equation of hyperbola. This equated with that value, that's the equation of hyperbola. But I'm interested on actually this part, delta t, because delta p I can calculate it from my data, from tx diagram. I can calculate the delta t, I can calculate t naught, which is very important to me. T naught can be calculated from the tx diagram. So let's expand this part. Let's try to expand this part. And how we can expand it? That's how we can expand it. Expanding is multiplied by itself. This parameter multiplied by itself, it becomes, this is how it becomes. It becomes t squared 2 t naught squared, t naught delta t plus delta t squared. If I expand this one. So from both sides, what I can cancel? T naught squared. So what is here? What's possible here at least? I can read out all of these values from the tx diagram. From where I can read the x? From the x-axis. The distance can be obtained from x-axis. The t naught can be calculated from y-axis. The delta t can be calculated from the extra time. That's the extra time. However, usually this value in terms of time is very small. Very, very small. Especially if the thickness of the layers are large and the separation between source and receiver is very small, that value is very small. So if I square it, what happens if you square a small value? It gets even smaller. Get very, very small number. So I can cancel it out. I can remove this one. And the final product, the final outcome is something like that. If I worked out, remove this, try to get delta t. So that's my delta t. But what I want the velocity. I can work out what is the velocity. The simple rearrangement of the equation. This equation, you come up with this equation. Why the approximate sign is there? Because I'm removing delta t squared. I'm removing delta t squared. So how I can calculate this equation? For example, for this simple hyperbolic line, how I can get the velocity of this layer, first layer. So it's basically delta t naught. T naught is read from here, from your data. Extra time is read from here. The x is read from the x-axis. Plug them in this equation to get the velocity of the first layer. So what's missing? We obtain velocity. What we still need? H. We need h as well. We need the thickness. They are too angry. Why? Because this is only for one layer. Yeah, but the ETH is not made up of one layer. It's made up of complex many layers. So how we solve it for multiple layers? Let me see, we still have some time. We will deal first of all with horizontal layers, because if the layers are dipping, the things get very, very complex. Things will not be easy. So for this course, at least, we do or deal with horizontal layers. We will not deal or obtain velocity for dipping layers. To deal with dipping layers, we need to do some extra advanced processing. We can either do migration or deep move out, which are a bit advanced, at least for your level. You have to take another course, applied one, then take data processing. So if there are multiple reflectors, we need to keep track at least of these times. Time at zero offset from first reflections, time at zero offset from second reflection, and third reflection, and so on, if I have multiple layers. And we work out from first velocity and move to deeper and deeper layers. That's how it works. And we will deal with something called RMS velocity. So if I go back, that's a velocity. This is the real velocity of layer 1. That's the real velocity of layer 1. Whereas for multiple layers, if this is a multiple layer, let's assume that this is how it goes. Snell's law, because the velocity is increasing, it deflects away. What you get V, total velocity, is not the velocity of a specific layer. It's the overall velocity. It's the total velocity. And that velocity, they call it RMS, root mean square velocity. So this is the velocity you get is not velocity of specific layer. So what is RMS velocity? And how we can work out what are the velocity and thicknesses of different layers. So we need at least to track these zero offset times. This is for the first reflections, second reflection, and so on. So this is just upside down. Here is the surface. What happened to this data? These are the real data. I move them upside down. So this reflection represents which layer here? This one? Yeah, that's one. This one is the second. This one is the last one. Which reflection for the same offset, for the same distance, which hyperbola have a larger delta t? First have a larger delta t. Delta t is decreasing. So the velocity for this layer, is it lower or larger? Is larger. The delta t is lower, so delta t is lower, it means velocity is large. Least time, faster velocity, where the delta t is here lower. We need to find, instead of two-way time, one-way time. You can work out the one-way time. Is it possible to find one-way time? Yes, if these are the data, that's the two-way time, whereas the one-way time is what? Basically, 2 times of this time, or this time divided by 2. That's one-way time. You can get this one from your data. These are your data. We need to keep track of these information. First of all, we need to find what are the one-way time. They can easily be found. So how we go around, we need to find what we call RMS velocity, root mean square velocity. It's for the first layer, the equation I showed you, it directly gives you the velocity of the first layer. However, for more than one layer, if you have multiple layers, you are trying to get the velocity of third or fourth layer, you need to know what we call RMS velocity. RMS velocity. So let me do some cleaning here. So basically the equation of RMS velocity V is square root of what we call, or sorry, not square root. Yeah, square root. That's Dex equation. So V, what we call sigma, or for two-layer case, let's assume for two-layer case only, not multiple layers, because I will give you an example of two-layer case. It's V1 squared plus, or time, T, dot T. It's not total time, it's rho, plus V2 squared T, that's T1, T2 divided by T1 plus T2. That's the sigma. So this is for how many layers? 2 layers. For 3 layers, what we add? V3 rho. This is one wait time within that layer. That's one wait time within only this layer. Then this is one wait time within this layer, not from here to here. Within this layer. And this is one wait time in the third layer. So that's what we call RMS velocity. So if I want that's velocity, RMS velocity of which layer is that? Second. If you want V3, then you add a 30. So let's try to find V RMS velocity of the first layer. What is the RMS velocity of the first layer? 1. Layer 1 equals square root of V1 squared rho 1 over. So what happens? This cancel, square will cancel. So RMS velocity of the first layer is actually the velocity of the first layer. But this, the other for 2-layer case, it cannot easily be simplified. You cannot simplify this one. That's the simplest form we have. So let's take an example. For 2-layer case, we need to find what is the velocity of the second layer using root mean square, or RMS velocity, root mean square velocity. So how it can be found? So these are our model. This is the model. We have 2-layer cases. We assume that's the first layer. That's then hyperbola from the second layer. We need to go from up down. From up down. First of all, we need to find the velocity of the first layer. So this velocity, I don't call it RMS. I can even call it RMS. Because we proved just now that RMS velocity of the first layer is the velocity of the first layer. So that's the velocity of the first layer. From where I can read this one, this value, delta t? From here. For the first layer. That's delta t at some x. Let's assume that's the x. This is the x. That's delta t. That's the x. And I know t naught. That's how I work it out. I obtained velocity 1. For the second layer, the velocity you are getting is not the velocity of the second layer. It's the RMS velocity. So this is this velocity, RMS, this velocity for the second one. So that's the velocity of the second. From where I can read these parameters to get the RMS velocity? From where the delta t is read? From here. From where t naught is, or t2 naught is read? From here. That's the time, total time. That's the total time. So that's the total time. I got what we call RMS velocity. So I need to bring velocity of the second layer. How I can get the velocity of the second layer if I know the RMS velocity? Where I should plug this number? Where I need to bring it? This equation. What I know T naughts, I know V1, I know these parameters, T naughts. I read them from the data. What's remaining? V2. V sub 2. That's what I need to know. So this is the RMS velocity of the second layer. I call it RMS velocity because not exactly velocity of second layer. That's not the velocity of the second layer, RMS velocity. So I obtain the velocity of the second layer. That's how it's done. So plug this number, RMS here. Everything is provided. You have velocity 1. You have T1 from here, and so on. You need to find out what's V2. So what about V3? I need to first find what's V1, then V2, then plug the RMS velocity of the third layer, this value, but for the third layer, in that equation, but add V3 and rho or tau 3 plus tau 3 for the third layer, and so on. It's very complex, isn't it? It's a bit, not very complex, but tedious job. Cannot be done if you have many layers. Cannot be done by hand. You need to have a software. Software can make these things easy if you have a software. In the software, what you do, you only pick these lines. You draw these lines. It needs only the travel time. And it will find out directly what's V1, V2, V3, and so on. You get some data. You need to do some picking. So picking is very important in geophysics, or at least in seismic techniques, with refraction or reflections. So that's how it works. For many layers, that's the equation you use actually. But let's assume that, for many layers we still use the same techniques. But let's assume that you want the velocity of a specific layer. We use what we call Dex Equation. That's Dex Formula. So Dex Formula states it's similar to RMS velocity, but it directly gives you the velocity of a specific layer. It gives you the velocity of a specific layer. So what's good about this one? We don't need to convert to one-way time. We can still use one-way time. Let's assume I want to get the velocity of the second layer. Let's assume I need to get the velocity of this layer, layer 2. So first I need to calculate the RMS velocity of bottom layer and RMS velocity of top layer, upper layer. RMS velocity are calculated using what equation? This equation. This is RMS velocity of first layer, second layer, and third layer. Third layer, you substitute their delta T of the third layer and T naught, T3 naught of the third layer from your TX diagram. So here, the velocity of this layer using the RMS equation or the velocity equation, simple velocity equations, and the time to this interface. That's the time to this interface. That's the time to what interface? This interface. First, here. And T bottom over T top. T bottom over T top. That gives you the velocity of this specific layer. They call this equation what? Dex equation. It's Dex equation. So you need the RMS velocity of lower layer, RMS velocity of upper layer. This, by the way, are similar to this. So Tn is this deeper layer here, this interface. Tn minus 1 is this one. So this is interface or time from second layer. That's the time from the first layer, bottom over top. That's what we call Dex equation. So I stop here. I think we covered good part. Let's just complete one thing, because how to get the thickness. We just calculate the velocity. How to calculate the thickness? Thickness is simply calculated by knowing the times and knowing the velocity of a specific layer. So if you know what is the velocity of a third layer, let's assume that that's the velocity of the third layer. We calculated it using the procedure we just explained. You need to know the time of this specific layer, 3, T0, and the time of an upper layer. You can read them from where? From here. So for this layer 3, let's assume that this is layer 2. There are 2 layer cases. So it's going to be this time here. This time exactly, you read it from here, minus this time. And the h is this h, total h, from here up until here. We are ignoring the third layer because this is the data for 2 layer cases only. Or no, sorry, there are 3 layer cases, 1, 2, 3. Yeah, there are 2 layer cases. So for this one, this is third layer, not, I got confused, I thought that there are 2 layers. Being very close to the screen is a bit tough. So this is going to be 3, that's going to be 2, this is H3, that's the total H. So rearrange the equation to get the thickness. Your book says or gives this equation, which is not exactly true. This gives that one-way time. It's not one-way time, it's two-way time. Because I'm dividing by 2, I'm canceling out with the one-way time. So that's for today, I believe. Do you have any questions?
Doctor,
yes.
how can we get the individual H?
Which one? In which part here, at least?
Yes, for each layer.
For the first layer is very simple. Yes, for the first layer you use with the equation. That's one. Yeah. For the second layer, you use this same equation. You already obtained the velocity of the second layer. So that's the time. From where? From here. From your data, you have this data. You acquire the data from the field. You made the picking. You came up to this final stage where you have the hyperbola. Some of you, I have started marking your last paper or last lab, and you used Excel to do plotting. So you can, if you make those, you pick these times, you can plot them in Excel, you get nice plots, similar to what you see here. And you can directly read what is T2, T02. You plug it here, and here it's going to be T01 divided by 2. You already know the velocity of the, which layer? Second layer. How about third layer? That's going to be what? T3, T2 divided by 2, and that's what? Velocity of HN is the thickness of that layer. It's not the total thickness. It's in between 2 layers. In between 2 layers. Within this zone. Yeah, it's very simple. This could be true in what sense? In the book, it could be true. What shall I change in this equation to make it true? Cancel the 2, yes. That's easy. If we are considering only one-way time, we just remove the 2. So the book says that, which is not exactly true. Yeah, but simple tuition tells you that this is correct. How I can get this thickness? Yeah, time here, divide them by 2. This difference and divide them by 2. So we'll discuss next some different topics, how we acquire data, and what is stacking, how we do stacking, and many, many other things. This is going to be a lab for the next week, and how we do stacking or velocity analysis. For this week, we will consider some simple data, seismic acquisition, You do it manually. Pick the velocity, pick the arrival times, then work out what are the thicknesses of layers and the velocity of different layers. Good? Any questions? So some students arrived a bit late. We were discussing when the midterm exam, going to be, and we came to the conclusion that the suitable week is week 8. So this is week 6. We'll have it in week 8. So I need to send, it won't be during lab time. Oh, sorry, either lecture time or lab time. No, it will be in some other time. Good?
Like in the evening?
Sometimes in the evening, yeah. So time that suits all of you.
But it should be a Sunday.
It will be in the same day, maybe at 5. We'll see how it works. We'll see. No? It includes up until this chapter. We'll conclude this chapter next week. The remaining part is simple. It's not, there is no much calculation, just some explanations and things. Some understanding, and finally we move to how we interpret and how we recognize whether there is hydrocarbon or not. We'll discuss also something about resolution, seismic resolution. So I stopped the recording.